We think we know what space looks like. Bright stars, glowing nebulae, epic cosmic colors. But here's the truth. Most of that is an illusion. If you were actually floating in space, without filters, without enhancement, it wouldn't look like a movie. It would look still, cold, and very, very dark. Space isn't pitch black, but it's far from colorful. Those stunning galaxy photos? They're enhanced. Not fake, just made visible. Because your eyes aren't built to see the kinds of light space is full of. Most of what's out there radiates in infrared, ultraviolet, X-rays. The human eye can't see those, so we assign them color to help us understand what's there. In reality, you'd see tiny white stars, a harsh bright sun, and a deep black canvas stretching forever. If you were near Earth, you'd see it lit on one side glowing blue and white, on the other, complete darkness. No twilight, no soft fade, just a sudden line dividing night from day. And the sun? It looks smaller than on Earth, but far more intense. No orange sky, no soft glare, just a blinding white disk in a black sky. And shadows? They're not soft in space. They're brutal. There's no atmosphere to scatter light. So it's either full sunlight or total darkness. Nothing in between. Now imagine standing on the moon. The surface is gray, rocky, jagged, not smooth like a cartoon. You look up, no blue sky, just stars. And Earth, suspended in place, never rising or setting. But even stars don't twinkle in space. They twinkle only when viewed through our atmosphere. Farther out, in deep space, you see less, not because there's nothing, but because everything is spaced so far apart, it all fades to pinpoints. No planets whizzing by. No galactic traffic. Just silence, darkness, distance. It's easy to forget how much emptiness space holds. Even in crowded parts of the universe, objects are light years apart. And yes, it's completely silent. Because space is a vacuum. No air, no medium, no sound. If two metal objects crash into each other in space, and you're watching it, you won't hear a thing. Unless you're physically touching something that vibrates, silence surrounds you. Let's talk about those colorful nebulas. In real life, they're faint. You might barely make out a soft glow with the naked eye, if you're lucky. But those Hubble images? They use long exposures and color filters to reveal what we can't naturally see. So yes, the color is real, but to your eyes, it'd be more like a wispy fog than a glowing canvas. Now drift toward Saturn, the rings? Absolutely there, but not metallic or overly bright. They're icy, translucent, and detailed, especially near the edges. Jupiter's clouds look pastel, not neon. It's still beautiful, just not exaggerated. And as you float past debris, rocks, or satellites, you realize how still everything feels. Even though it's all moving, at thousands of kilometers per hour, motion in space feels slow because distances are so vast. Out here, there's no up, no sound, no color-corrected magic, just reality. Pure, raw cosmic silence. If you kept going far beyond planets, past Pluto, out of our solar system, you'd eventually look back. And Earth? A pale dot. Carl Sagan called it a mote of dust suspended in a sunbeam. And that's exactly how it looks. Tiny, fragile, floating in a sea of black. So, what does space really look like? It's emptier than we imagine, darker than we think. But it's also full of forces of motion, of light we can't see. It's not what we see in movies. It's not colorful and loud. It's quiet, unimaginably vast, and deeply humbling. This is what space really looks like. What if I told you the entire universe began from a single invisible point? No galaxies, no stars, no time, not even space itself. Just nothing. Then, in a fraction of a second, Everything but began. This is the story of how the universe was born and how it gave rise to everything we know. About 13.8 billion years ago, the Big Bang happened. But it wasn't an explosion in space. It was an expansion of space itself. Space, time, energy, and matter all came into existence. In less than a second, the universe expanded faster than the speed of light. We call this moment inflation. From something smaller than an atom, the universe grew to astronomical size in a blink, and it was hot, unimaginably hot. Trillions of degrees. Particles of matter and antimatter were created and destroyed in flashes of energy. As the universe expanded, it began to cool. This cooling allowed particles to slow down and combine. First quarks, then protons and neutrons, and eventually hydrogen and helium, the first elements of the cosmos. Light still couldn't travel freely. The universe was a thick fog of charged particles. But 380,000 years after the Big Bang, atoms finally formed, and the universe became transparent. That ancient light, the cosmic microwave background, still travels through space today. We can see it with special telescopes. It's the baby picture of the universe. Now gravity took over. Tiny imperfections in the early universe began to grow. Clouds of hydrogen collapsed under their own gravity and ignited. The first stars were born. These early stars were massive, hundreds of times the mass of our sun. They lived fast and died young. When they exploded as supernovas, they created new elements: carbon, oxygen, iron. These elements were the building blocks of everything: planets, oceans, and even life. Millions of stars grouped into galaxies. Over billions of years, galaxies merged and evolved. One of them became our home, the Milky Way. About 4.6 billion years ago, in a quiet corner of this galaxy, a cloud of gas began to collapse. From it, our sun was born. Around the sun, dust and debris formed planets, including Earth. Earth was violent and molten. A collision with a Mars-sized object created the moon. Volcanoes raged. Asteroids bombarded the surface. But over time, things cooled. Oceans formed. And somewhere in those oceans, life began. At first, life was simple: single cells, tiny organisms. But evolution worked slowly and steadily. Cells learned to work together. Plants appeared. Animals followed. Eventually, creatures crawled onto land, and millions of years later, humans arrived. You, me, we are stardust, made from atoms forged in dying stars. Today, the universe is still expanding. But here's the strange part: it's accelerating. We don't know why. We call it dark energy, a mysterious force that makes up most of the universe. As galaxies move farther apart, the night sky will grow darker. One day, stars will burn out, black holes will evaporate, and the universe could end in cold, endless silence, a fate called heat death. Or maybe it will collapse in a big crunch. Or perhaps something entirely unexpected will happen. But for now, we are here, alive on a small planet, circling a yellow star, in one galaxy among trillions. We are part of this vast story. 13.8 billion years in the making. The atoms in your body are ancient, some as old as the Big Bang. You are a way for the universe to understand itself. So the next time you look up at the stars, remember, this isn't just space. It's your origin story. And it's still unfolding.
Is time travel possible in our universe? Have you ever wished you could glimpse the future, or perhaps right or wrong from the past? The idea of time travel, jumping through the fourth dimension, has captivated humanity for centuries. But is it just the stuff of science fiction blockbusters, or could it genuinely be a reality in our universe? Today, we're diving deep into the fascinating, and sometimes paradoxical, world of time travel. The astounding truth is, we are all time travelers, constantly moving forward at a rate of 1 second per second. But what if we could speed up or slow down that journey? According to Albert Einstein's theories of relativity, time isn't a constant, universal ticker. It's relative, and it can be affected. The key concept here is time dilation. Einstein's special theory of relativity, published in 1905, tells us that the faster you move through space, the slower you experience time relative to someone stationary. This isn't just theory, it's a proven fact. One of the most famous early experiments demonstrating time dilation involved atomic clocks. In 1971, the Havlicek experiment flew highly precise cesium beam atomic clocks around the world on commercial airplanes, one eastward and one westward. When they returned, they were compared to a stationary atomic clock at the U.S. Naval Observatory. The clocks on the planes were indeed slightly behind or ahead, exactly as predicted by relativity, by mere nanoseconds, but undeniably, this minuscule, unmeasurable difference confirmed that motion affects the passage of time. This effect is even crucial for our everyday technology. To GPS satellites orbiting Earth at an altitude of about 20,200 kilometers (12,550 miles) move at speeds of approximately 14,000 kilometers per hour (8,700 miles per hour) relative to the ground. If their internal clocks weren't constantly adjusted for both special and general relativistic effects, they would drift by roughly 38 microseconds per day. This seemingly tiny error would quickly accumulate, causing GPS systems to become inaccurate by several kilometers per day, making navigation impossible. This constant calibration is a testament to the reality of time dilation. It's not just speed that can warp time. Einstein's general theory of relativity, published in 1915, introduces another profound time-bending factor: gravity. The stronger the gravitational field, the slower time passes for observers within that field, relative to those in weaker fields. This means time moves infinitesimally slower at sea level, where gravity is slightly stronger than it does on top of a very tall mountain. Again, this has been experimentally verified with incredibly precise atomic clocks. For example, experiments at the National Institute of Standards and Technology (NIST) had shown that an atomic clock placed just 30 centimeters, about 1 foot higher than another, will tick ever so slightly faster. We're talking about a difference of nanoseconds, but it's a measurable and consistent effect. So, standing on a massive planet, or even more dramatically, near a neutron star or a black hole, would genuinely slow down your personal clock relative to someone far away. So, time travel to the future is undeniably possible and even an everyday reality for astronauts. Astronauts on the International Space Station (ISS), orbiting at speeds of 28,000 kilometers per hour (17,500 miles per hour), experience time slightly slower than us on Earth. While the effect is minuscule, about 0.01 seconds over 6 months, it means that ISS astronauts are technically traveling into Earth's future, albeit by a tiny fraction of a second. If you could travel close to the speed of light for an extended period, or spend time in an extremely strong gravitational field, you would age slower than people on Earth. When you returned, you would have traveled significantly into their future. Consider the famous twin paradox. If one twin embarked on a round trip to a distant star at near light speed, while the other remained on Earth, the traveling twin would return to find their Earthbound sibling much older. For a journey to a star 20 light-years away at 99.999% the speed of light, the space twin might only age a few months, while the Earth twin would have aged over 40 years. The biggest challenge for significant future time travel is the immense energy required to accelerate a spacecraft to such relativistic speeds. We're talking about energy equivalent to the output of entire stars. The most extreme example of gravitational time dilation would be near a black hole. As you approach a black hole's event horizon, the point of no return, the gravitational pull becomes so incredibly intense that time would appear to slow to an almost complete stop for an outside observer. For someone falling into it, however, they would continue to experience time normally, accelerating towards the singularity in what would feel like a finite amount of their own personal time. This is a one-way trip, of course. Once past the event horizon, nothing, not even light, can escape. So, while a black hole could be a powerful future time machine for the outside universe, it's not a round-trip ticket. Now, for the big question, can we travel to the past? This is where things get truly speculative and fraught with paradoxes. While the mathematics of general relativity does allow for some exotic spacetime geometries, known as closed time-like curve CTCs, that could theoretically enable backward time travel, we have no empirical evidence or practical means to achieve it. These theoretical constructs often involve highly improbable conditions or materials that may not exist in our universe. One popular theoretical concept for backward time travel is a wormhole, also known as an Einstein-Rosen bridge. Imagine folding a piece of paper and punching a hole through it, connecting to distant points directly. A wormhole would be a shortcut through spacetime, potentially connecting not just different locations, but different points in time. Theoretically, if one end of a traversable wormhole one you could actually pass through were moved at near light speed, or placed in a strong gravitational field, time dilation would occur, creating a time difference between its two mouths. Stepping through could then, in theory, lead to the past or future. However, creating and stabilizing such a wormhole would require immense amounts of exotic matter with negative energy density. This is matter that would behave repulsively, essentially propping open the wormhole, and we have no idea how to produce it or even if it genuinely exists outside of mathematical theory. Furthermore, even if such matter exists, containing and manipulating it on a cosmic scale is beyond our wildest current technological dreams. Beyond wormholes, other highly theoretical concepts for manipulating spacetime to allow for past travel include rotating black holes, like Kerr black holes, which theoretically could allow for CTCs, and even cosmic strings. Cosmic strings are hypothetical one-dimensional topological defects in spacetime, incredibly dense and thought to be remnants from the early universe. Some theoretical models suggest that two cosmic strings whipping past each other at high speeds could, in principle, bend spacetime sufficiently to allow for backward time travel. However, like wormholes, these ideas require extreme conditions and materials that are currently purely hypothetical. The biggest roadblock to past time travel isn't just technology, it's causality. If you could go back in time and change the past, it could lead to impossible paradoxes. The most famous is the grandfather paradox. What if you went back in time and prevented your grandparents from meeting, thus preventing your own birth? If you were never born, you couldn't have gone back in time to stop them, meaning they would have met, and you would have been born. A logical contradiction that breaks the fabric of cause and effect. Another mind-bending paradox is the bootstrap paradox, also known as an ontological paradox. This occurs when an object or piece of information travels back in time and becomes the cause of its own existence, with no discernible origin. Imagine a scientist from the future goes back in time and gives Isaac Newton a copy of his own published Principia Mathematica. Newton then uses this book to develop his theories and publish his work, which eventually ends up in the hands of the future scientist. Where did the original knowledge of calculus and gravity come from? It would have no true beginning, caught in an infinite, self-sustaining loop. Physicists have proposed ways around these paradoxes, though they remain hotly debated. One idea is the many worlds interpretation of quantum mechanics, suggesting that every time a choice is made or an event occurs, the universe splits into multiple parallel universes. So, if you went back and killed your grandfather, you would simply create a new, branch timeline where you were never born, while your original timeline remains untouched. Another concept is the Novikov self-consistency principle, which proposes that the laws of physics would simply prevent any paradox from occurring. No matter how hard you tried to change the past, some event would always conspire to prevent it, ensuring consistency. You might try to prevent an event, only to inadvertently cause it, or some unforeseen accident prevents your intervention. Despite the tantalizing theories and the captivating allure of science fiction, current scientific consensus is that time travel to the past remains highly improbable, if not outright impossible, given our current understanding of physics, the immense energy requirements, the need for exotic matter, and the unresolved paradoxes present formidable barriers. Stephen Hawking famously held a party for time travelers, but sent out the invitations after the party. No one showed up, which he cited as empirical evidence against backward time travel. While telescopes allow us to see into the past by observing light from distant galaxies that took billions of years to reach us, actual physical travel to previous moments in time is a different beast entirely. So, while we are all perpetually time traveling into the future at varying rates, thanks to Einstein's profound insights into relativity, journeying to the past remains a captivating dream of science fiction. The universe, in its elegant complexity, seems to guard its past with an unbreakable lock, that the pursuit of understanding time's mysteries continues to push the boundaries of human knowledge and imagination. Who knows what future discoveries might reveal, or what new dimensions of time we might one day comprehend. Thanks for watching, and keep questioning the fabric of reality.
For decades, we've looked up at the red planet and asked the same question. Is there, or was there, life on Mars? Not flying saucers or little green men, but even the tiniest microbial life would change everything we know about the universe. And here's the truth. Mars is leaving behind clues. Let's start with what we do know. Mars once had water. Not a few drops, but rivers, lakes, maybe even oceans. We found dried-up riverbeds, sediment patterns, and minerals that only form in the presence of water. Where there's water, there's a chance for life. NASA's Curiosity and Perseverance rovers have been digging into Martian soil for years, and the results are interesting. They've discovered organic molecules, the building blocks of life. Not life itself, but the kind of chemistry life needs to get started. In 2020, scientists confirmed that salty liquid water may still exist beneath Mars' surface. Hidden underground and briny, but present. And that's key, because if life exists on Mars today, it's probably not on the surface. Mars is harsh. It's cold, dry, and blasted with solar radiation. Its atmosphere is 100 times thinner than Earth's, and it doesn't protect against UV rays. So any surface life would have a hard time surviving. But beneath the surface, that's where things get interesting. Underground, life could be shielded from radiation. It could stay warm from geothermal heat. And there may be enough liquid water to sustain it. Think microbial life. Simple, tiny organisms may be similar to extremophiles here on Earth. On our planet, life exists in some of the harshest places imaginable. Bacteria thrive in boiling hot springs. Fungi grow inside nuclear reactors. And deep beneath the Antarctic ice, microbes live in salty, oxygen-poor lakes. So is it really that far-fetched to think something similar could exist on Mars? Let's go back millions, even billions of years. Mars once had a thick atmosphere. It had flowing water. It had a magnetic field. In many ways, it was Earth-like. So what happened? Scientists believe Mars lost its magnetic field, which allowed solar winds to strip away the atmosphere. As the air thinned, water evaporated, and the planet dried out. Temperatures dropped. Radiation increased. It became the Mars we know today. But what if life began before all that? What if microbes thrived in Martian lakes and oceans, only to retreat underground as the surface became uninhabitable? It's possible they're still there, dormant, hiding, waiting. That's why NASA's Perseverance rover is exploring the Jezero crater. It used to be a lake, and its river delta may have preserved signs of ancient life. Perseverance is collecting rock samples right now, and one day we'll bring them back to Earth for study. If we find fossilized microbes, it would be one of the most important discoveries in human history. It would mean life isn't unique to Earth. It would mean the universe might be full of it. So, what would life on Mars look like? Forget complex creatures. Think simple. Bacteria, algae, maybe something totally unknown. It wouldn't need sunlight, just warmth, water, and chemistry. It might glow, like some deep-sea life here on Earth, or be colorless, slow-moving, and built for survival. But here's the twist. If life evolved independently on Mars, it might not be like anything we've ever seen. Different DNA, different biology. A second origin of life right next door. And if we don't find life, that's just as important. It helps us understand the limits of habitability. It shows how rare or fragile life might be. Either way, the question shapes our future. Because if life once existed on Mars, it might exist elsewhere, on Europa, Enceladus, or beyond. And if Mars is lifeless, then Earth becomes even more precious than we thought. So every rock we study, every drill we take, every rover we send, it's not just about Mars. It's about understanding life itself. And who knows? Maybe one day, it won't be just robots searching. Maybe we'll walk those dusty plains ourselves, looking for answers in person. Until then, Mars keeps whispering clues. And we keep listening.
Imagine looking up at the night sky, knowing that orbiting the very closest star to our sun is a planet that might, just might, harbor alien life. It sounds like a dream, or perhaps the plot of an epic science fiction movie. But this isn't fiction. This is Proxima Centauri b, and it's sending ripples of excitement through the scientific community. Today, we're diving into why this tiny world is such a huge deal in the hunt for life beyond Earth. For decades, scientists have theorized about planets orbiting other stars, known as exoplanets. It wasn't until 1995 that the first exoplanet orbiting a Sun-like star was confirmed. Fast forward to 2016, and a monumental discovery was made right on our cosmic doorstep. Astronomers confirmed the existence of Proxima Centauri b, a planet orbiting Proxima Centauri, which is part of the Alpha Centauri triple star system and, crucially, the closest star to our Sun at just 4.2 light-years away. That's roughly 40 trillion kilometers. Proxima Centauri itself is a red dwarf star, much smaller and cooler than our Sun. It's only about 12% the mass of the Sun and significantly dimmer, emitting far less light and heat. While this might sound like a disadvantage, it means its habitable zone, the region where liquid water could exist on a planet's surface, is much closer to the star. Proxima b orbits its star at a mere 7 million kilometers, 4.3 million miles, which is less than 5% of the Earth-Sun distance. Despite this closeness, because Proxima Centauri is so dim, Proxima b receives roughly 65% of the light energy that Earth receives from the Sun, making its average temperature potentially suitable for liquid water. So, what do we know about Proxima b itself? It's classified as a super-Earth, meaning it's slightly more massive than Earth, with an estimated minimum mass of about 1.07 Earth masses. Its orbital period is incredibly short, just 11.2 Earth days, meaning a year on Proxima b flashes by in less than 2 weeks. One of the biggest questions is whether Proxima b has an atmosphere. Given its close proximity to a red dwarf, it faces intense stellar flares and radiation. Red dwarfs are known for their frequent and powerful flare activity, which could potentially strip away a planet's atmosphere or irradiate its surface. Another fascinating aspect is the likelihood of tidal locking. Because it orbits so close to its star, Proxima b is very likely tidally locked, just like our moon is to Earth. This means one side of the planet would perpetually face star, experiencing eternal daylight and extreme heat, while the other side would be in perpetual darkness and extreme cold. However, scientists theorize that a thick atmosphere could distribute heat around the planet, leading to a terminator zone, a twilight region between the hot and cold sides, where conditions might be more temperate and potentially support liquid water. The presence of liquid water is considered the holy grail in the search for life as we know it. Scientists are using powerful telescopes and developing new instruments to look for signs of water vapor, oxygen, methane, or other biosignatures in Proxima b's atmosphere. However, directly observing the atmosphere of such a small planet orbiting a bright star is incredibly challenging. It's like trying to spot a firefly next to a lighthouse from hundreds of miles away. The advent of next-generation telescopes is crucial for these investigations. The James Webb Space Telescope, JWST, with its incredible infrared capabilities, is already being used to characterize exoplanet atmospheres. Though Proxima b is particularly difficult for it due to the glare from its star. Future telescopes, such as the proposed extremely large telescope Elton Chile, currently under construction, will have mirrors up to 39 meters, 128 feet, in diameter. These giants will be able to directly image exoplanets and analyze their atmospheres with unprecedented detail, potentially providing definitive answers about Proxima b's conditions. One of the major hurdles for life on Proxima b is the extreme activity of its host star. Red dwarfs like Proxima Centauri are prone to frequent and powerful stellar flares, which are sudden bursts of radiation that are far more intense, relative to the star's total output, than those from our Sun. A 2021 study observed a superflare from Proxima Centauri that was 100 times more powerful than any flare ever observed from our Sun. Such events could repeatedly sterilize a planet's surface or erode its atmosphere over billions of years, making the emergence and sustenance of life incredibly difficult. Despite the harsh surface conditions, some scientists hypothesize that life on Proxima b might exist subsurface. If the planet has a geological activity or subsurface oceans, life could thrive in environments shielded from the harsh stellar radiation. Similar scenarios are considered for moons in our own solar system, like Europa, Jupiter, or Enceladus, Saturn, which are thought to harbor subsurface oceans beneath icy shells, potentially warmed by tidal forces. Even if we detect gases like oxygen or methane in Proxima b's atmosphere, it doesn't automatically mean life. These biosignatures can also be produced by non-biological geological or chemical processes. Scientists would need multiple lines of evidence and a deep understanding of the planet's unique environment to confidently claim the presence of life. It's a complex puzzle, requiring careful analysis to avoid false positives and ensure any claims of life are robustly supported by data. It's crucial to clarify that NASA, nor any other space agency, has confirmed the existence of life on Proxima Centauri b. While it remains a highly exciting and promising target for astrobiological research, all current evidence only suggests its potential for habitability, not the actual presence of life. The search continues, and every new observation brings us closer to understanding whether our nearest exoplanet neighbor is truly a haven for life. The excitement is real, but the definitive confirmation of alien life is still a goal for the future. Proxima Centauri b stands as a testament to the incredible diversity of planets in our galaxy and the persistent human drive to find life beyond Earth. It challenges our assumptions about what makes a planet habitable and pushes the limits of our observational capabilities. While the internet might get abuzz with rumors, the scientific process is slow, meticulous, and requires irrefutable evidence. Today, we truly confirm life on another world will be one of humanity's greatest milestones. And Proxima b is certainly a Factcy in that historic race. Thank you for joining us on this cosmic exploration. Imagine a future so distant, so profoundly quiet, that it defies our wildest imagination. We're talking about the ultimate end of everything we know, the slow, silent demise of the universe itself. Today, we're not just looking into the future of humanity, but into the chilling, inevitable fate of the cosmos. Prepare to witness a cosmic funeral unlike anything you've ever conceived. The most widely accepted theory for the universe's ultimate fate is heat death. This isn't an explosion or a dramatic collapse, but a gradual, inexorable fading away. It's dictated by the second law of thermodynamics, which states that the entropy, or disorder, of a closed system like our universe must always increase. Eventually, all energy will be evenly distributed, meaning there will be no more available energy to do work. Imagine a perfectly mixed cup of coffee. No hot spots, no cold spots, just uniform lukewarmness, a state of maximum entropy. For billions of years, gravity was the dominant force shaping the universe, pulling matter together to form stars and galaxies. But about 5 billion years ago, something shifted. The expansion of the universe, which began with the Big Bang, started to accelerate. This acceleration is attributed to a mysterious force called dark energy, which now makes up about 68% of the universe's total energy density. Dark energy is essentially pushing galaxies further and further apart, overcoming gravity's pull. Our universe currently basks in the glow of countless stars, but this won't last forever. Stars like our Sun burn through their hydrogen fuel via nuclear fusion. Our Sun is about halfway through its 10 billion year lifespan, with roughly 5 billion years left before it swells into a red giant and then shrinks to a white dwarf. Smaller, cooler stars called red dwarfs, which are much more common, burn their fuel incredibly slowly. They can last for trillions of years, with the smallest ones living for up to 10 trillion years or more. But even these cosmic embers will eventually exhaust their fuel and fade away. Once all the stars have burned out, the universe will enter a degenerate era. The only objects left will be stellar remnants, white dwarfs, neutron stars, and black holes. White dwarfs, the remnants of sun-like stars, will cool down over unimaginably long timescales, eventually becoming black dwarfs, cold, dark, and theoretical objects, as the universe isn't old enough for any to have formed yet. Neutron stars, the incredibly dense cores of once massive stars, will continue to exist, but they'll be silent and dark. The universe will become an increasingly desolate place, lit only by the occasional faint glow of cooling stellar corpses. Eventually, the largest and most dominant structures remaining will be black holes. These gravitational behemoths will slowly grow by consuming any remaining matter that happens to fall into them, including each other. Galaxies will merge, and their central supermassive black holes will combine to form even larger ones. However, even black holes are not eternal. According to Stephen Hawking's theory of Hawking radiation, black holes slowly evaporate over unfathomably long periods. This process is incredibly slow for stellar mass black holes, taking up to 1067 years for a solar mass black hole to completely evaporate. Supermassive black holes, like the one at the center of our galaxy, Sagittarius *, could take up to 10,100 years to fully disappear. After black holes have evaporated, what's left? Only a vast, empty expanse of incredibly diffuse particles. Even protons, the building blocks of atomic nuclei, are theorized to eventually decay, though with an incredibly long half-life, estimated to be at least 1034 years, possibly much longer. If protons do decay, then eventually, all matter as we know it will cease to exist, leaving only a sea of photons, neutrinos, electrons, and positrons, spread out thinly across an ever-expanding universe. As the universe expands due to dark energy, it will also get progressively colder. The cosmic microwave background radiation CMB, The leftover heat from the Big Bang currently sits at a frigid 2.7 to 5 Kelvin, about 270 Celsius or 455 Fahrenheit. As the universe expands, this radiation will stretch and cool further, approaching absolute zero. The empty space between particles will become vast beyond comprehension, and the temperature will plummet to near absolute zero. While heat death is the most probable scenario, other intriguing, though less likely, theories exist. The Big Rip suggests that if dark energy continues to strengthen and its density increases, it could eventually overcome all fundamental forces. First, galaxies would be torn apart, then stars and planets, and eventually, even atoms themselves would be ripped into their constituent particles. This scenario, if the conditions were right, could happen in as little as 22 billion years in some models, but current data suggests dark energy is constant, making the Big Rip unlikely. Another fascinating, albeit unsettling, possibility is false vacuum decay. Our universe might currently be in a false vacuum state, meaning it's not in its lowest possible energy state. If a true vacuum bubble were to spontaneously form somewhere, it would expand at the speed of light, converting everything it touches into a different, more stable reality. This would be an instantaneous, universal catastrophe, completely altering the laws of physics as we know them. Regardless of the exact mechanism, the end of the universe, particularly through heat death, paints a picture of ultimate cosmic desolation. Star formation will cease. Galaxies will become isolated islands, expanding away from each other so rapidly that they will eventually disappear from each other's observable universe. The very concept of forever takes on a new, chilling meaning. Time will continue, but nothing will ever happen. No new stars, no new life, no new thoughts, just an endless, silent, dark expanse. The thought of the universe ending in such a slow, silent, and desolate manner, certainly humbling. It reminds us of the precious, fleeting nature of the cosmic era we currently inhabit, an era teeming with stars, galaxies, and life. While these cosmic timescales are almost incomprehensible to us, understanding them deepens our appreciation for the vibrant, energetic universe we currently call home. It's a reminder to cherish the light before the long, eternal night. Thanks for watching, and remember to look up and marvel at the universe while it's still alive.